So just a quick note before I start the video. During recording I've messed up the recording software, just experimenting a while, so that's why the video format looks a bit weird. You'll see like this black bar above and everything. I'm sure it won't happen again. I do apologize on that, and as well the audio mic quality. I'm going to try and get that fixed. Enjoy the video. Hello, welcome back. In this video we'll be looking at RC series circuit and LR series circuits. Let's begin. When a resistor is placed with a capacitor connected with a DC power source, we call this an RC charging circuit. So if I have my power source here, resistor, capacitor here, we can call this our charging circuit. But if we inserted a switch, so that's the electrical schematic, the time required for a capacitor to be fully charged is equivalent to 5 RC. We can display this using this chart. This is a chart off a website. I'll be sure to link it in the description. So as you can see here, at 5 RC, our voltage is roughly nearly 100% already, and this is what we'll count it as just being fully charged. So let's do a quick example using the formula we just discovered. So if your R is T equals RC, where T equals time, R equals resistance, C equals capacitance, and let us say, for example, R equals 10k. Just go right over there. There we go. 10k ohms, and RC equals 1000 microfarads. So we want to find out how long will it take for our capacitor to charge up. So we substitute our values into there. So 10,000 times 1000 times 10 to the power minus 6. I have to convert it to farads, the SI units. That gives us 10 seconds. It'll take 10 seconds for our capacitor to be fully charged up. So I just want to give a quick visualization here with the table I showed you before. And this is how it looked like if we did a quick graph. So this is just a quick graph I just drew up. And as you can see, at the 0.7 time constant, we have 50% of our capacitor charged up. So that would be over here. So highlighted and so it's over here. Come to 1 time constant, 1 RC, we have 63% of our voltage charged up. Notice our current is decreasing as voltage increases. Come to our 2 time constant, 86, 3 time constant, 95. Our 4 time constant is 98% over here. And this is already when our capacitor is at a steady state. So between this area, it's only when we reach to our 5 time constant that we can say that our capacitor is fully charged. This is at 99.3%. This is already fully charged, and we will need to bother anymore. So this area. So I'm just going to talk briefly on the discharging of a capacitor. You might be curious that we just spoke about charging, and it's just with the graph you saw earlier, it's just reverse of that really. On same table, it's in the same website. I'll link it in the description. As you can see here, even after 0.5 time constant, our voltage has dropped significantly from our 90%. So already down to 60.7% here. And this is just from 0.5, so here. And we keep going down here, we get 49.7, 36.8, 13.5, 5, 1.8. They come down to after 5 time 0.7. And when we reach here, this is when we say our capacitor is fully discharged. just very brief. Maybe you're wondering, how do we use this? This is our newfound knowledge. And I'll give you a quick example here. Let's say Bob. This is our good friend Bob. Bob has the tendency to eat snacks at 3 AM. He likes them cookies. So he goes in there, he's on a weight loss program, but he can't help it. So he goes there, finds them, and he opens them. You know, and you live with Bob. You're sick and tired of Bob. He keeps eating these cookies, and you know they're yours, and you want the best for him. He wants to lose weight. You're trying to help him. So to prevent this, and you know when he's eating cookies, you can set an alarm to know you, to identify you. Oh, he's eating cookies at 3 AM. So there's a quick circuit I've drawn out, and when the door is closed, this is a normally open switch. So that when the door is closed, our switch is open. You know, there's no voltage or anything going through this, current, sorry, whatever, going through this. Nothing. It's, you know. So when Bob opens the fridge, or opens the fridge, our switch is then closed. This causes everything to go in. You know, current can now travel, there's a voltage, and we can time this. So, you know, we can wait a while. Is he just grabbing something else or what? Wait a while, we can set this to 10 seconds, you know, 30 seconds, or maybe just instantly, you know, just depending. Because we've learned this, our new time constant formula, we can set this circuit up, we can have it connect to an LED, so when the switch goes, this goes off, or we can have an alarm, also in parallel, have an alarm go off. So last but not least, we'll talk about the LR series circuits, so our inductor resistor series circuit. And similar to the RC circuit, if we put a resistor in series with an inductor, we get an RL circuit, and the time constant of this circuit is time it takes for the current to reach its maximum value for the inductor. So as you know, in the inductor, as mentioned in our previous inductance videos, I can't remember if I did 1 or 2, we said that the inductor opposes current. So so we have that, we have our inductor, and that. So we can calculate this by using this formula. So, you know, T equals time, L equals inductance, R equals resistance. So here's the graph for the current below, for the inductor. And as you see, the graph is quite similar to the capacitor one, which we had shown. And as it remains the same, you see it takes 5 time constants for this to build up. So we get that steady value of current and almost no voltage, because if you remember from the previous video, it opposes current and it produces a, you know, opposing voltage at each of the inductor's poles. And when this current reaches that steady value, that voltage is no longer, there. So we can do a quick example of this to solidify our knowledge, as I quite like to do. And so we'll get our formula, T equals L over R. And let's say we have a 40 millihenry inductor and a 5 ohm resistor. What will be the time constant for this circuit? We substitute our values in here. So remember, it's in millihenry, you convert it to henries, SI units. Since it's already ohms, we don't need to change it. Put 5 down there. Do we work that out? You should get 8 milliseconds. So take 8 milliseconds for our inductor, 1 time constant. One time equals 88 seconds. Alright, thank you for watching. Hope you learned something. Please do leave a comment on the new video format if you like it. Whatever. Alright, see you next time.